Hey guys, it is Campbell. So today we are going to be talking about taking the derivative of transcendental functions. Let me first address the elephant in the room. My hair is very flat today. I just got off work. Please ignore it. I know it looks horrible. Don't leave comments saying mean things because I'll cry. So let's get right to it. Firstly, this term transcendental. You may not have heard of it before. Maybe your calculus teacher threw it around in class without you fully understanding what it is. So let's go over that first. A transcendental function is a function that is different from what you might see in, an algebra class. In algebra, you might see something like x cubed minus 3x squared plus 4. This is an algebraic function. It is, generally easy to solve, easy to graph with particular points on the graph. A transcendental function, an example of a transcendental function would be something like the natural log of x. This is something that cannot be described using a finite number of polynomial terms. If you're in Calculus 2, then you probably know about infinite series, and you can describe this and other non-polynomial functions with infinite series. But with a finite number of polynomial terms, these can never be fully accurately described. So let's talk about these transcendentals. Just as a side note, in this video, I'm going to be showing you the derivatives of common transcendental functions, and then I'm going to be showing you how these derivatives can be found, whether it be through first principles or through other means, and then I'm going to give us a few practice problems to go over. So we're going to be starting with the natural log of x. It is a pretty common one. The derivative of the natural log of x is simply 1 over x. Now this seems a little weird because it's not algebraic, obviously, because it is 1 over x, x to the minus 1. It has a negative exponent, but from a transcendental, we get something that looks sort of algebraic. So let's go back to first principles, the limit definition of a derivative, and let's discuss how we get this answer, because it does seem a little weird. So if you'll remember all the way back to first principles, we know that the derivative is simply the limit as h goes to 0 of f of x plus h minus f of x all over h. So we have the natural log of x plus h minus the natural log of x all over h. Now looking at this, we can recall from our algebra class that this is simply a difference of logarithms, so we can further simplify this to give us the limit as h goes to 0 of the natural log of x plus h all over x all over h. Well, to me, once again, we've got a sum over x. We can simplify this further, and we will get the limit as h goes to 0 of the natural log of 1 plus h over x over h. Now we're getting somewhere with this. From here, it's going to take a bit of a weird turn because there is another definition we need to solve this. So up here, I'm going to write the definition of Euler's constant E, which you, I'm assuming, have heard of at this point. So we're going to use this to solve a few problems today. So the definition of Euler's constant E is actually the limit as n goes to 0. I'm probably not writing that big enough. Let me fix that. Is the limit as n goes to 0 of 1 plus n all to the 1 over n power. That is Euler's constant. So looking at this, I don't know, I feel like we can get it into a form that is pretty similar to that. Let's go ahead and try. So let's take h over x to be equal to n. So we know that h is going to be equal to x times n. And we know that 1 over h is equal to 1 over x times n. And so because we've now got h and x in terms of n, let's go ahead and remind ourselves that as h goes to 0, because once again we're taking the limit as h goes to 0, what is going to happen to n? Well, as h goes to 0, no matter what x is, n is going to be 0. So as h goes to 0, n also goes to 0. Let's go ahead and take this. The limit as n goes to 0. And now let's replace these terms. So I'm going to simplify this to be 1 over h times the natural log of 1 plus n but we know that 1 over h is the same thing as 1 over x times n. So let's go ahead and replace this with x times n. Now we know that because of our logarithm properties, that this is the same thing as raising our inside term of the logarithm to this exponent. So we now have the limit as n goes to 0 of the natural log of 1 plus n to the 1 over x times n. We know that 1 over x times n is the same thing as 1 over x times 1 over n. And we know that our exponential properties allow us to, since they're being multiplied, it means it's an exponent being raised to an exponent. So we can pull this 1 over x out. Once again, we will get the limit as n goes to 0. When we pull this 1 over x out, it goes as another exponent, which we can take back to the front. So the limit as n goes to 0, 1 over x times the natural log of 1 plus n all to the 1 over n. But now we have limit as n goes to 0, 1 over x. Since we are taking the limit of n, x might as well be a constant. So we're going to ignore this 1 over x term. The natural log of 1 plus n all to the 1 over n. Well, again, since natural log has nothing to do with the n, we're basically just taking the limit as n goes to 0 of this inside term, 1 plus n to the 1 over n, which is exactly the limit definition of e, which means this limit is equal to 1 over x times the natural log of our inside term, e. The natural log of e is, of course, 1, which means that the derivative of the natural log is 1 over x. And now we have used first principles with, a minor bit of algebraic manipulation to conclude that the derivative of natural log of x is indeed 1 over x. So next up, we're going to talk about Euler's function, e to the x. The derivative of this function, which you may know already, sometimes in calculus this stuff is introduced at different times. Not all of the transcendentals are covered together, but you may know at this point that the derivative of e to the x is simply itself, e to the x. That's pretty curious, right? So again, we are going to use first principles, and we are going to derive this. Once again, let's go ahead and start. We'll start over here. So we've got the limit as h goes to 0 of f of x plus h, which of course is going to be e to the x plus h minus e to the x all over h. Now, because of our properties of exponentials, this e to the x plus h is the same as e to the x times e to the h. minus e to the x, which means we can pull an e to the x out to give us e to the x times the limit as h goes to 0, e to the h minus 1 over h, running out of space here. Sorry if that's a bit small. Now, e to the h minus 1 over h. Well, we're going to do sort of a similar process here, so you're going to have to bear with me once again. We are going to once again let the numerator be equal to n. So, change color here. Let's make it easier to see. So we will let e to the h minus 1 be equal to n. So we know, therefore, e to the h equals n plus 1. And we know that the natural log of e to the h is equal to the natural log of n plus 1. Okay. And this, of course, is just equal to h. Since we have the natural log of e to the h, the e's will cancel out, and it will just leave us with h. So, coming back, we'll go ahead and... So we're going to bring this down. We've got e to the x times the limit as n goes to 0, because once again, we're going to be working in terms of n now. We've got n over the natural log of n plus 1. Bear with me once again, we're going to do a bit of funky algebraic manipulation. We're going to multiply the top and bottom by 1 over n to give us e to the x times the limit as n goes to 0 of 1 over n times the natural log of n plus 1. Once again, we're starting to see it. This is the same thing as e to the x times the limit as n goes to 0, 1 over the natural log of 1 plus n to the 1 over n. And so, of course, this is going to give us e to the x times. Once again, we've got the natural log. What's inside is the definition of e. And so it's going to give us 1 over the natural log of e, which, of course, will give us e to the x as the derivative of itself. All right, so I'm in a different place with a different outfit on. What happened? You'll never know. What a shame. All right, so now we're going to be covering the derivative of exponential functions. I've got 2 to the x here, but this is going to be this more or less the same with any function, any arbitrary a to the x. So this is going to be very similar to e to the x. The only difference is this derivative is going to be equal to itself, 2 to the x, times the natural log of 2. That's pretty interesting. And it sort of makes sense if the derivative of e to the x is simply e to the x. Well, that's the same thing as e to the x times the natural log of e. And in fact, when we solved it out, we showed why exactly that is. So once again, we're going to go back to our first principles here. We will say the limit as h goes to 0 for 2 to the x plus h minus 2 to the x all over h. Once again, we already know we're going to pull our 2 to the x out, bring it to the front. So this is going to give us the limit as h goes to 0 of 2 to the x times 2 to the h minus 1 all over h. All right, so from here we're going to do something very similar where, we'll write it over here, we are going to let 2 to the h minus 1 be equal to n, our handy little variable n, which means 2 to the h equals n plus 1. Now, last time we did the natural log of both sides because we were working with base e, but here, if we work with the log base of 2, log base 2 of 2 to the h is the same as h, which is the same as the log base 2 of n plus 1. Go ahead and try and section that off to the side here. All right, so we've got that h is equal to log base 2 of n plus 1. We've got that our top 2 to the h minus 1 is equal to n, so we're going to move back over here. We know that this is going to be the limit as h goes to 0 of 2 to the x times n over log base 2 of n plus 1. All right, making progress. Now, once again, we are going to multiply our top and bottom by 1 over n. Do a bit of algebraic manipulation, but we'll get there. So we've got the limit as, oh, and I apologize, this should be the limit as n goes to 0. Once again, as h approaches 0, then we are going to have 2 to the 0 is 1, minus 1 is going to be 0. So as h approaches 0, n also approaches 0. So this should be the limit as n approaches 0. We've got the limit as n approaches 0 over here of 2 to the x times, and again, we're going to multiply the top and bottom by 1 over n. Hopefully you can see that all right. So this is going to be 1 over n times the log base 2 of n plus 1. All right, and we know our logarithm properties. This is going to be a power for what is inside of our logarithm. So this is, I'll move the 2 to the x to the outside. 2 to the x times the limit as n goes to 0, 1 over log base 2 of 1 plus n all to the 1 over n. All right. So the limit as n goes to 0. Well, we know that log base 2 is going to mean nothing, just like our last proof with e to the x. So the limit as n goes to 0 of simply 1 plus n to the 1 over n is, of course, going to be e. So this should give us 2 to the x times the limit as n goes to 0 of 1 over log base 2 of e. Well, we're certainly getting closer to our answer. Let's go ahead and see here. We've got 2 to the x times, we have gotten rid of our limit, so it's going to be 1 over log base 2 of e. Well, you know what, to me, I see another logarithm property here. Remember that if we have, I'll write this in a different color so it is more obvious to see. Remember that if we have log base a of b, this is the same thing as the natural log of b over the natural log of a. It does not have to be the natural log. It can be in any base, but I think that the natural log is going to make things a bit easier for us. So this is the same thing as 2 to the x times 1 over natural log of e over natural log of 2. All right, and now, because we've got 1 over another fraction, we're going to flip the natural log of 2 to be on top. Natural log of e is, of course, 1. And so finally, this will give us 2 to the x times the natural log of 2. Thus, it is proved that the derivative of 2 to the x is 2 to the x times the natural log of 2. Once again, this can be generalized for any function. Once again, I'll write this in a different color. For any function a to the x, if we take the derivative, it is going to give us a to the x times the natural log of a. So, derivative of any function a to the x will give us a to the x times the natural log of a. There we go. Okay, so from here on out, you can relax. We're not going to be using first principles. We're not going to be using limit definition of a derivative anymore. But things might get a little more, you might think that they're complicated. They're going to get even less intuitive. The limit definition is, I think, the most intuitive definition of a derivative. If you want the instantaneous rate of change, then you take the change between 2 points as that difference becomes 0. This is a little bit less intuitive. We're working with trig now, inverse trig. I'm assuming at this point that you have all covered your basic trigonometric derivatives, sine, cosine, tangent, cosecant, cotangent, secant. So hopefully we've got all that covered. I'll go ahead and give it to you. So the derivative of arctangent is 1 over x squared plus 1. Pretty weird. We have a trigonometric, and we're getting more or less an algebraic function as the derivative. This is weird, right? How can we think about this? Well, if this is a function, we'll say it's a function of y. So we'll say, well, I guess a function of x in terms of y. So we'll say that y equals arctangent of x. What does this tell us about y, though? What does it tell us more precisely? What does it tell us about x in terms of y? Well, of course, we've got tangent inverse. So it tells us that the tangent of y is equal to x. All right. So now we've got a function of x in terms of y. What if we try and derive this with respect to y, right? If we say, dx dy, what is that going to be equal to? Well, the derivative of tangent is, of course, secant squared. So secant squared of y is dx dy. Cool. And this tells us if we, now, as you get to higher and higher level math, I don't know, they will treat it differently. They will say, a differential is not a fraction, but a differential can be treated as a fraction, and it just works. So for every single intent and purpose, a differential is a fraction, and you can take that to the bank. So if we flip this fraction, we say dy dx, change in y with respect to x, then this should be equal to the reciprocal of this, right? If we treat this as a fraction, we put dy on top, then this is going to be the same as 1 over the secant squared of y, which is, of course, the cosine squared of y. Okay, but what is this all telling us, right? We've got all this information down. What does it actually tell us? Well, obviously trig has to do with triangles. So what if we go ahead and make a right triangle here? And because we've got our tangent of y, we'll go ahead and call this angle y. Now, if tangent of y is equal to x, and we know that tangent of any angle theta is equal to the ratio of the opposite side to the adjacent side lengths, then if tangent y is equal to x, we know our opposite side must be x, and our adjacent side is therefore 1, right? X over 1 was just going to give us x. Well, we need to find the cosine squared of y to find our derivative, right? So cosine is the adjacent side over the length of the hypotenuse. So we need to find the length of the hypotenuse. So of course we know that x squared plus 1 squared is of course just 1 is going to be equal to c squared. And therefore we know that the hypotenuse is going to be the square root of x squared plus 1. All right, so cosine squared, we have 1 over the cosine by itself. Cosine is just going to be 1 over the square root of x squared plus 1. But if we square it, once again, cosine squared, then we've got 1 squared on top is just going to be 1, and the square root of x squared plus 1 all squared on bottom. Well, since we're squaring a square root, those are just going to cancel out. And it will leave us with 1 over whatever is left underneath the radical, x squared plus 1. Man, isn't that so cool? We did not use first principles. We did not use any sort of weird algorithm to try and find this. We just simply used what we know from geometry about angles and triangles to find the derivative of the arctangent function. So next up, we're going to try and find arcsine. This process, I'll give you a hint, is going to be similar. I want you to take a minute, try and find the derivative of arcsine on your own. Of course, if you don't already know it. If you're watching this video and you already know what they are, hey, welcome. Thanks for stopping by, even though you already know this stuff, or maybe you're reviewing. But if you don't, try yourself to use a similar method to what we did with arctangent to try to find the derivative of arcsine of x. I'll go ahead and give you a second, pause the video, and come back when you're ready. So, of course, once again, I'm going to start off by saying if y is equal to the arcsine of x, then the sine of y is going to be equal to x. Therefore, dy is going to be cosine of y. Therefore, dy dx is going to be equal secant of y. Because once again, if we treat the differential like a fraction, which it definitely is, then we simply take the reciprocal of cosine, which is secant. So now if we go ahead and draw our perfect right triangle, and we take this angle to be y, well, if sine of y is equal to x, then we know that sine is opposite over hypotenuse, the ratio of the opposite side length to the hypotenuse side length, which means that the opposite side is going to be x and the hypotenuse is going to be 1, which means we need to figure out our adjacent side. So this should hopefully be simple. We know that x squared plus, we'll call our adjacent side a squared, must be equal to 1, which means that a squared is equal to 1 minus x squared, which means that a must be equal to the square root of 1 minus x squared. Okay, so we have our adjacent side, the square root of 1 minus x squared. Easy. So now our derivative in terms of x, which of course is going to be dy dx up here, is going to be the reciprocal of the cosine of y, which means it's going to be the hypotenuse over the adjacent side, which means that our derivative of arcsine of x is going to be hypotenuse 1 over adjacent, the square root of 1 minus x. Squared, that is. My apologies. There we go. So we know that our derivative of arcsine is 1 over the square root of 1 minus x squared. I don't think I'll ever get tired of that. Man, that is just so cool. Using purely algebra, well, I suppose we did have to use a bit of calculus here. We have to know what a derivative is, but 90% of our work is done in terms of geometry, and we can figure out these derivatives. Now, as much as I would like to sit here all night and derive all of these derivatives of these functions with you, I think that, after a while, especially for the trigonometric ones, you get into the cycle where, all right, you understand it, you make the triangle, you follow the steps, and then you find the derivative. And it's pretty easy. So I've given you a list of all of the derivatives just as a review. Derivative of natural log of x is 1 over x. Derivative of e to the x is e to the x. The derivative of a to the x is a to the x times the natural log of a. Arctangent is 1 over x squared plus 1. Arcsine is 1 over the square root of 1 minus x squared. Arccosine is negative 1 over the square root of 1 minus x squared. It's the same thing as arcsine, but negative. Arcsecant is 1 over, this one's a little bit more weird, 1 over x times the square root of x squared minus 1. Arccosecant is sort of the same deal with sine, where it is the same thing as arcsecant, but negative. And for arccotangent, of course, the same thing as arctangent, but negative. So I'm going to leave these up there, but we are going to go ahead and do some practice problems. So for this first problem, I want you to find the derivative of, let's see, we'll go ahead and do the natural log of arcsine of x. Go ahead and take a minute, pause the video, find the derivative of this, and come back when you are ready. All right, so welcome back. Hopefully the answer that you got is 1 over arcsine of x times the square root of 1 minus, or rather, 1 over the whole thing, arcsine x times square root 1 minus x squared. This is the chain rule, so we've got a natural log, so it's going to be 1 over whatever is inside the natural logarithm times the derivative of the inside. Derivative of arcsine x is, of course, 1 over the square root of 1 minus x squared. So we've got 1 over arcsine times 1 over the square root of 1 minus x squared, and that gives us 1 over arcsine x square root 1 minus x squared. All right, for this next practice problem, try and find the derivative of arcsecant of 3 to the natural log of x. This is a pretty big chain rule, but don't worry, if you want an even bigger, better one, wait till the end of the video, and we'll have a pretty good one. So go ahead, take a minute, pause the video, find the derivative of the arcsecant of 3 to the natural log of x. All right, so welcome back. Once again, we're doing arcsecant of 3 to the natural log of x. So another chain rule, we're going to start with our outside function, arcsecant of x. The derivative of arcsecant is 1 over x times the square root of x squared minus 1. But it is a chain rule, so we've got a u in here. So it's actually going to be 1 over u, square root of u squared minus 1 times the derivative of u. So we've got 1 over our u term, 3 to the natural log of x times the square root of 3 to the natural log of x squared, or 3 to the 2 natural log x minus 1. And this is, of course, times the derivative of the inside term. So the derivative of a to the u is a to the u times the natural log of a times the derivative of u. So we've got 3 to the natural log of x times the natural log of 3 times the derivative of u, which is 1 over x. So our final answer should be the natural log of 3 times 3 to the natural log of x, all over x times 3 to the natural log of x times the square root of 3 to the 2 natural log of x minus 1. So honestly, it's not too bad, right? It's just chain rule is where most people mess up, so we're going to make sure to get some practice in. This next one is going to be a bit simpler. We're going to find the derivative of arctangent of x all to the minus 1. Go ahead, take a minute, pause the video, and find the derivative of that, and come back when you have your answer. All right, welcome back. This one, once again, not too bad. Another chain rule. So it's a power rule. We take our power to the front and then subtract 1 from the power to give us negative arctangent of x to the negative 2. Once again, multiplied by the derivative of the inside function, which is arctangent of x, so 1 over x squared plus 1. So this will give us negative 1 over arctangent squared of x times x squared plus 1. All right, and finally, this last one is going to be a big one. It is going to be, we're going to be finding the derivative of the arccosecant of the natural log of 2 to the arctangent of e to the x. Pause the video, take as much time as you need. Let's go ahead and find this derivative. All right, welcome back. So once again, as long as you have a good grasp on the chain rule, this one is really not that bad. I know it looks ugly, I know it's long, but honestly, it's not horrible. So first of all, we have arccosecant of this function u. So our derivative of arccosecant is negative 1 over u times the square root of u squared minus 1. So negative 1 over our u is natural log of 2 to the arctangent of e to the x. So negative 1 over the natural log of 2 to the arctangent of e to the x times the square root of that whole thing squared, natural log of 2 to the arctangent of e to the x squared minus 1, multiplied by the derivative of this first inside term, natural log of x. So 1 over 2 to the arctangent of e to the x times the derivative of this inside term, which is going to be itself 2 to the arctangent e to the x times the natural log of 2, times the derivative of this inside term. The derivative of arctangent of x is 1 over x squared, or 1 over u squared plus 1. So we've got 1 over e to the x squared, or e to the 2x plus 1, times the derivative of this last inside term, e to the x, which is, of course, itself. So all of our numbers which are not strictly denominators, that is going to be e to the x, the natural log of 2, and 2 to the arctangent of e to the x. Those are all going to be in our numerator, and all of this is going to be in our denominator. So our final answer should be negative e to the x times the natural log of 2 times 2 to the arctangent of e to the x all over 2 to the arctangent of e to the x times e to the 2x plus 1 times, let me close that off there, the natural log of 2 to the arctangent of e to the x times the square root of the natural log of 2 to the arctangent of e to the x squared minus 1. There we go. Final derivative of the video. I hope this video was useful. I hope that walking through some of these methods, whether it be through first principles or using triangles, what we know about geometry and calculus, to figure out these derivatives more, I guess, graphically maybe. I hope that was useful. If you have any questions, leave a comment. If I made any mistakes in any of these calculations or anything, let me know, because I did just do these off the cuff. I made them up. I did not have them scripted or anything. Well, at least I didn't have the practice problem scripted. I did work through all of this beforehand. But yeah, so if you notice anything that I made a mistake on, go ahead and let me know. But yeah, I think that's going to be it for this video. Let me know what else you guys would like to see. Please leave a like and consider subscribing if this is stuff that you are interested in. And I hope to see you guys next time. Bye.